All right, so standing waves. As you saw in the slinky exercise today, standing waves are waves where you end up with kind of a constant pattern happening in a medium that has a wave, that can support a wave. So for example, if we have a string, and you guys managed today to get something that looked a little bit like this. Most of you managed to get one of these. Where in this area, the particles, that part of the slinky, were going up and down like that. And in this area, they were doing the same thing. We call that an antinode. And then in this region here, the particle really wasn't moving. You could actually stand on both sides, and it would never touch you. That's the idea behind a standing wave. Now what's happening there is this constructive and destructive interference are setting up so that they always happen at a certain point. And really what you're doing is you're taking two waves. Let's draw a couple of transverse waves here. You're sending one, when you send a wave down to the end and it reflects, the next wave is coming along and they run into each other. And when they hit each other, if they hit each other at this orientation, then you're always going to cancel out. If you look at this from the rest position, at any point in here, we go up about the same distance that we go down. So they cancel out. You get constructive interference at that point. On the other hand, if they're out of phase, then that doesn't happen. So what you're doing is you're setting it up so that destructive interference always happens in the exact same spot, and constructive interference happens in the same spot. And there are rules around how that works. And what we're working on here is we're working on situations. The first situation is going to be what we call two fixed ends, which would be like your slinkies where you're holding both ends. You have to have a node at both ends. You have to have the equivalent of destructive interference at both ends, or it doesn't work. If you have something that's completely open, like a wind tunnel, clarinet would be an example, or a flute, then you have to have an antinode at the two ends, or again, it doesn't work. And you have to, the only way that works is if the length of the object and the length of the wavelength, match up in a certain way. So we're going to talk about that now, how to figure that out. We'll start with two fixed ends. So with two fixed ends, this would be like a great example would be a guitar string. If you pluck a guitar string, it doesn't move. The ends don't move. So you're forcing a node there in those two spots. And if you can set things up so that you always have that node, imagine drawing an actual transverse wave on here. So if we drew a transverse wave that looked like this, then the nodes are in the right place. However, if we drew one that looked like this, the node's right over here, but it doesn't fit here. So this would not maintain itself. And you saw that when you were trying to set the standing waves. Sometimes you got waves that just didn't work. This is what's happening. When you manage to set up a node at both ends, that's when you got a standing wave. And the situations that occurs are nicely illustrated in this picture from the old textbook. The first situation is when you have one antinode in the middle and a node at both ends. So node, node, and antinode. Now if you look at that, to trace one of these into a full wavelength, you would have to extend it past to double its length. So really what we're saying here is that the length of this is equal to 1/2 of the wavelength that you're setting up to get that standing wave. The next one down, if you were to trace out a wave in this one, you would manage to get the full wave inside that length. So in this case, the length is equal to 1 wavelength. All right, that's the next situation where you can get a node at both ends. Going further, and some of you managed to do this, if you have 3 spots, so 3 antinodes, 1 node, an antinode, 2 nodes, 3 nodes, 4 nodes, and 3 antinodes. If you trace this one out, you get 1 wavelength plus another 1/2. So the length of this string is 3 lambda over 2, or 1.5 wavelengths. And there are 2 ways you can arrange this. You can either change the length of the string and keep the wavelength the same, or you can keep the length of the string the same and change the wavelength. So there is a formula for a standing wave with two fixed ends, but I don't even know it. I don't use it. I just use these diagrams. I draw the diagram quickly and work out the relationships that way. Oops. So those are the three sets. So you get the lowest point is length is equal to half of lambda over 2. The second one is equal to lambda. And the third one, the length has to be equal to 3 lambda over 2. And as you can see, each time it's going up by half a wavelength. So that is the relationship. Now, an important thing to get is, as long as you don't change the density or anything else, the speed stays the same. So if you keep the length of the string the same, but in one case it's half a wavelength, in another case it's a full wavelength, then you've reduced the wavelength itself. If you look up here, this wavelength is a lot bigger than the one that fits on here, right? If you reduce the wavelength, you increase the frequency. Think of a guitar string. You shorten the frequency, shorten the length, you change the frequency. Okay, you get a different sound. We'll talk a little more about that one in class. Let's go quickly through the other two situations. Two free ends. So open at both ends. What this means is you have to have an antinode here and an antinode here. So any situation you can set up where you have an antinode at both ends works. Anything else doesn't work. Excuse me. So if you picture your standing wave model, you get something like this. Terribly drawn, but that's okay. These are antinodes, and these are nodes. The first place where you can actually get an antinode of both ends is if you do that. Cut it right at that spot. So let's draw that into the diagram. We have an antinode and an antinode. And one node in the middle. So again, if we were to take this and extend it into one full wavelength, then, excuse me, we could see that we're taking, again, half of a wavelength here. So when the lowest point is half a wavelength. The next spot, if we get a little bigger, would be to here, this range. Now to draw that one in, I'm going to move this one out. To draw that one in, I'll do it in red. You have to have 2 nodes. Sometimes it's easier if you're trying to draw this to think of it in terms of the number of nodes. Now, if you look at this, we're managing to fit one full wavelength inside this arrow, inside this space. So the second case is going to be the length of the pipe is the wavelength. So let's see if we can smooth a whole lot out. Third situation, and I'll only take it that far because beyond that it starts to get a little bit daft to try and draw them all in. We have 3 nodes fitting, so I'm going to go to the top, to the bottom, to the top, to the bottom again. Like that. And again, if you look at this, we have a wavelength that's there, and then another half for the next part. So it's lambda over 3 lambda over 2, 1.5 wavelengths. And that's it. So it follows the same pattern when you have 2 free ends. The only difference is antinode at the end. So if it's a fixed end, it has to be a node. If it's a free end, it has to be an antinode. And we're going to take that into the next step, which is what I call a closed column, in which case we have a closed end, or a fixed end, and an open end. And as you can probably guess, that means we have to have a node here and an antinode here, and any combination that allows those 2 things to happen is the right one, where it works, sets up a standing wave. So let's draw in our standing wave model here. If we start with a node, so we'll start at the fixed end, the first place we get an antinode is right there, 1/4 of a wavelength. So that's going to look like this. And the length is equal to lambda over 4. 1/4 of a wavelength, and it fits. The next one I'll do with the green line. Well, let's work our way along. Here's the next place we have an antinode. So we're going to get 3/4 of a wavelength. So we're going to start, go up and down. So start, go up and down, and up. There's the next point. Three-quarters of a wavelength. And to take it one more, just to make it look nice and crazy in there, we're going to go from a node, first antinode, second antinode, third antinode. So we're going to do something like this. 2, 3. Pretend I do that right. So now we've got one wavelength to here, and another quarter wavelength here. So, and you might have already guessed this, 5/4 of a wavelength is the length of that pipe. And that pretty much covers it. Again, you can work out the speed is going to stay the same when you increase these wavelengths, so the frequency has to change. And we'll talk about the variations on that tomorrow. Last thing, I'm going to pause it right here. You can have a look at this. This is a layout of how this works, either changing the length of the pipe or changing the wavelength of the sound. 2 different ways of doing the exact same thing. See you tomorrow.